Hello everyone. So today we're gonna talk about Google PageRank algorithms. Alright. So ever wonder how Google works? Let's take a look at the search button. So if you search for the word dog, you might assume that Google simply scans all web pages to see how many times they mention dog and then list the results based on that frequency. This approach, known as a text-based ranking system, is how Google initially operated. However, consider this: a page that repeats the word dog a million times isn't very useful. In contrast, a site that offers a variety of information about different dog breeds is far more helpful. To address this issue and provide more relevant search results, Google developed the PageRank algorithm, among others, to improve the way it ranks pages. So, now let's see why modeling for PageRank algorithms. Here we have 3 reasons. The first is information overload. Without a systematic way to rank pages, users would be overwhelmed with low quality or irrelevant information, as the order of results would seem random rather than based on value or trustworthiness. The second is objective ranking. So, the PageRank algorithm represents the link structure as a network of pages interconnected by directed links, with each link serving as a vote of confidence. However, not all votes hold the same value. Links originating from pages with high authority given greater significance. So, for the last one is link has a measure of trust. So, links between pages imply value, acting as endorsement or recommendations in the network. This is where the concept of links as votes or endorsements becomes essential. When one page links to another, it's often because the author believes the destination page is valuable or trustworthy. So for the next, let's see. The internet is made up of many web pages, each containing information on its page. Each page may also contain links to other pages. From here, we can see that they have 1, 2, 3, and 4 pages, and we also include each link, which means that, for example, page 1 has a link to each of the other 3 pages. So each link receives 1 per 3 of pages importance. Page 2 has 2 links. So page 3 and page 4 each receive 1/2 of each page 2. So from here we have this modeling. So it is important. And then when you can see here, Sij 1/1 pi I links to page 1. So this is a stochastic matrix because all the entries are positive. So for the next is why eigenvectors and eigenvalues. The goal of PageRank is to find a steady state vector for the entire network of web pages. So this stretching factor is called the eigenvalue. In the context of the PageRank transition matrix P, we are looking for an eigenvector R associated with an eigenvalue of 1. This gives us P dot R is equals to R. So next, we would see other concepts working in tandem with linear algebra. There are 3, which one is Markov chain. So Markov chain is a stochastic process that satisfies the Markov property, a memoryless property. So this where we can say that satisfy the Markov property, where the probability of future behavior is independent of past behavior. So the internet network matrix can also be defined by using the transition probability, where each entry can be described as the odds that a web server would follow a link to page, given that they were on page. So as ij is equals to pxt is equals to pjxt minus 1. So another thing is the damping factor. So the damping factor is actually set around 0.85, meaning there's an 85% of chances that a user will keep following links on the current page, and a 15% chance they will randomly jump to a new page on the web. And the last one is the graph theory, where we use this graph theory to identify our eigenvector. So next will be the application. So for the application, here we have page A, page B, page C, page D. So from here we can see that we can have these matrices which each link to 1 per third, 1 per 2, and then from here we can say that AX is equals to 1x, where here 1x, this one is A, matrix A, this one is X, and this is 1 because of our eigenvalue, and this is our X. So where the vector is S1, S2, S3, X4. So from here we can get the system equation, and then we have this system equation. We just have to substitute the x2 to make it in 1, which is x1. So from here we can derive, we will get x1 over 12, 12, 4, 9, 6, where we will say that 12, 4, 9, 6 is actually the vector. So now we have to multiply with 1 per 31 because of its eigenvalue is 1, and 31 is the total sum of 12 plus 4 plus 9 plus 6. We will get 31, and the final answer would be the PageRank vector. So from here we would can conclude which page is in high rank. So when we see here 0.387, which is page A, is in high ranking, which is more relevant. So when you search something, it will appear first, the link will appear first, and follow with the second ranking, which is page C, 0.290, and the last ranking, which is very less accurate, is 0.129, which is page B. So that's all from me. Thank you. Hopefully it helpful for others as well.